Energy is the capacity that objects or substances have to perform work or produce changes in the environment. It is a force that drives and enables things to happen. Energy is the quantitative property that is transferred to a body or to a physical system, recognizable in the performance of work and in the form of heat and light. Energy is a conserved quantity. The law of conservation of energy states that energy can be converted in form, but not created or destroyed. The unit of measurement for energy in the International System of Units, SI, is the joule, J. Forms of energy include the kinetic energy of a moving object, the potential energy stored by an object, for instance due to its position in a field, the elastic energy stored in a solid object, chemical energy associated with chemical reactions, the radiant energy carried by electromagnetic radiation, the internal energy contained within a thermodynamic system, and rest energy associated with an object's rest mass. These are not mutually exclusive. All living organisms constantly take in and release energy. The Earth's climate and ecosystems processes are driven primarily by radiant energy from the sun. The energy industry provides the energy required for human civilization to function, which it obtains from energy resources such as fossil fuels, nuclear fuel, and renewable energy. Forms. In a typical lightning strike, 500 megajoules of electric potential energy is converted into the same amount of energy in other forms, mostly light energy, sound energy, and thermal energy. Thermal energy is energy of microscopic constituents of matter, which may include both kinetic and potential energy. The total energy of a system can be subdivided and classified into potential energy, kinetic energy, or combinations of the two in various ways. Kinetic energy is determined by the movement of an object, or the composite motion of the object's components, while potential energy reflects the potential of an object to have motion, generally being based upon the object's position within a field or what is stored within the field itself. While these two categories are sufficient to describe all forms of energy, it is often convenient to refer to particular combinations of potential and kinetic energy as its own form. For example, the sum of translational and rotational kinetic and potential energy within a system is referred to as mechanical energy, whereas nuclear energy refers to the combined potentials within an atomic nucleus from either the nuclear force or the weak force, among other examples. Energy, in physics, the capacity for doing work. It may exist in potential, kinetic, thermal, electrical, chemical, nuclear, or other various forms. There are, moreover, heat and work, i.e., energy in the process of transfer from one body to another. After it has been transferred, energy is always designated according to its nature. Hence, heat transferred may become thermal energy, while work done may manifest itself in the form of mechanical energy. All forms of energy are associated with motion. For example, any given body has kinetic energy if it is in motion. A tension device such as a bow or spring, though at rest, has the potential for creating motion. It contains potential energy because of its configuration. Similarly, nuclear energy is potential energy because it results from the configuration of subatomic particles in the nucleus of an atom. Energy can be neither created nor destroyed but only changed from one form to another. This principle is known as the conservation of energy or the first law of thermodynamics. For example, when a box slides down a hill, the potential energy that the box has from being located high up on the slope is converted to kinetic energy, energy of motion. As the box slows to a stop through friction, the kinetic energy from the box's motion is converted to thermal energy that heats the box and the slope. Energy can be converted from one form to another in various other ways. Usable mechanical or electrical energy is, for instance, produced by many kinds of devices, including fuel-burning heat engines, generators, batteries, fuel cells, and magneto-hydrodynamic systems. In the International System of Units, SI, energy is measured in joules. 1 joule is equal to the work done by a 1 Newton force acting over a 1 meter distance. Energy is treated in a number of articles. For the development of the concept of energy and the principle of energy conservation, see Principles of Physical Science, Mechanics, thermodynamics, and conservation of energy. For the major sources of energy and the mechanisms by which the transition of energy from one form to another occurs, see coal, solar energy, wind power, nuclear fission, oil shale, petroleum, electromagnetism, and energy conversion. The word energy derives from the ancient Greek, neuro gamma epsilon iota alpha, Romanized, energia, lit. Activity, operation, which possibly appears for the first time in the work of Aristotle in the 4th century BC. In contrast to the modern definition, energia was a qualitative philosophical concept, broad enough to include ideas such as happiness and pleasure. In the late 17th century, Gottfried Leibniz proposed the idea of the Latin, vis viva, or living force, which defined as the product of the mass of an object and its velocity squared. He believed that total vis viva was conserved. To account for slowing due to friction, Leibniz theorized that thermal energy consisted of the motions of the constituent parts of matter, although it would be more than a century until this was generally accepted. The modern analog of this property, kinetic energy, differs from vis viva only by a factor of 2. Writing in the early 18th century, Émilie du Châtelet proposed the concept of conservation of energy in the marginalia of her French-language translation of Newton's Principia Mathematica, which represented the first formulation of a conserved measurable quantity that was distinct from momentum, and which would later be called energy. In 1807, Thomas Young was possibly the first to use the term energy instead of vis viva, in its modern sense. Gustave Gaspard Coriolis described kinetic energy in 1829 in its modern sense, and in 1853, William Rankine coined the term potential energy. The law of conservation of energy was also first postulated in the early 19th century, and applies to any isolated system. It was argued for some years whether heat was a physical substance, dubbed the caloric, or merely a physical quantity, such as momentum. In 1845 James Prescott Joule discovered the link between mechanical work and the generation of heat. These developments led to the theory of conservation of energy, formalized largely by William Thomson, Lord Kelvin, as the field of thermodynamics. Thermodynamics aided the rapid development of explanations of chemical processes by Rudolf Clausius, Josiah Willard Gibbs, and Walther Nernst. It also led to a mathematical formulation of the concept of entropy by Clausius and to the introduction of laws of radiant energy by Joseph Stephan. According to Noether's theorem, the conservation of energy is a consequence of the fact that the laws of physics do not change over time. Thus, since 1918, theorists have understood that the law of conservation of energy is the direct mathematical consequence of the translational symmetry of the quantity conjugate to energy, namely time. In the International System of Units, SI, the unit of energy is the joule. It is a derived unit that is equal to the energy expended, or work done, in applying a force of 1 Newton through a distance of 1 meter. However, energy can also be expressed in many other units not part of the SI, such as ergs, calories, British thermal units, kilowatt-hours, and kilocalories, which require a conversion factor when expressed in SI units. The SI unit of power, defined as energy per unit of time, is the watt, which is a joule per second. Thus, 1 joule is 1 watt-second, and 3,600 joules equal 1 watt-hour. The CGS energy unit is the erg and the imperial and US customary unit is the foot-pound. Other energy units such as the electron volt, food calorie, or thermodynamic kcal, based on the temperature change of water in a heating process, and BTU are used in specific areas of science and commerce. In 1843, English physicist James Prescott Joule, namesake of the unit of measure, discovered that the gravitational potential energy lost by a descending weight attached via a string was equal to the internal energy gained by the water through friction with the paddle. Some forms of energy. Mechanical, the sum of macroscopic translational and rotational kinetic and potential energies. Electric, potential energy due to or stored in electric fields. Magnetic, potential energy due to or stored in magnetic fields. Gravitational, potential energy due to or stored in gravitational fields. Chemical, potential energy due to chemical bonds. Ionization, potential energy that binds an electron to its atom or molecule. Nuclear, potential energy that binds nucleons to form the atomic nucleus, and nuclear reactions. Chromodynamic, potential energy that binds quarks to form hadrons. Elastic, potential energy due to the deformation of a material, or its container, exhibiting a restorative force as it returns to its original shape. Mechanical wave, kinetic and potential energy in an elastic material due to a propagating oscillation of matter. Sound wave, kinetic and potential energy in a material due to a sound propagated wave, a particular type of mechanical wave. Radiant, potential energy stored in the fields of waves propagated by electromagnetic radiation, including light. Rest, potential energy due to an object's rest mass. Thermal, kinetic energy of the microscopic motion of particles, a kind of disordered equivalent of mechanical energy. Energy may be transformed between different forms at various efficiencies. Items that transform between these forms are called transducers. Examples of transducers include a battery, from chemical energy to electric energy, a dam, from gravitational potential energy to kinetic energy of moving water, and the blades of a turbine, and ultimately to electric energy through an electric generator, and a heat engine, from heat to work. Examples of energy transformation include generating electric energy from heat energy via a steam turbine, or lifting an object against gravity using electrical energy driving a crane motor. Lifting against gravity performs mechanical work on the object and stores gravitational potential energy in the object. If the object falls to the ground, gravity does mechanical work on the object, which transforms the potential energy in the gravitational field to the kinetic energy released as heat on impact with the ground. The sun transforms nuclear potential energy to other forms of energy. Its total mass does not decrease due to that itself, since it still contains the same total energy even in different forms, but its mass does decrease when the energy escapes out to its surroundings, largely as radiant energy. There are strict limits to how efficiently heat can be converted into work in a cyclic process, e.g. in a heat engine, as described by Carnot's theorem and the second law of thermodynamics. However, some energy transformations can be quite efficient. The direction of transformations in energy, what kind of energy is transformed to what other kind, is often determined by entropy, equal energy spread among all available degrees of freedom, considerations. In practice, all energy transformations are permitted on a small scale, but certain larger transformations are not permitted because it is statistically unlikely that energy or matter will randomly move into more concentrated forms or smaller spaces. Energy transformations in the universe over time are characterized by various kinds of potential energy that has been available since the Big Bang, being released, transformed to more active types of energy such as kinetic or radiant energy, when a triggering mechanism is available. Familiar examples of such processes include nucleosynthesis, a process ultimately using the gravitational potential energy released from the gravitational collapse of supernovae to store energy in the creation of heavy isotopes, such as uranium and thorium, and nuclear decay, a process in which energy is released that was originally stored in these heavy elements, before they were incorporated into the solar system and the Earth. This energy is triggered and released in nuclear fission bombs or in civil nuclear power generation. Similarly, in the case of a chemical explosion, chemical potential energy is transformed to kinetic and thermal energy in a very short time. Yet another example is that of a pendulum. At its highest points the kinetic energy is zero and the gravitational potential energy is at its maximum. At its lowest point the kinetic energy is at its maximum and is equal to the decrease in potential energy. If one, unrealistically, assumes that there is no friction or other losses, the conversion of energy between these processes would be perfect, and the pendulum would continue swinging forever. Energy is also transferred from potential energy to kinetic energy and then back to potential energy constantly. This is referred to as conservation of energy. In this isolated system, Energy cannot be created or destroyed, therefore, the initial energy and the final energy will be equal to each other. Energy gives rise to weight when it is trapped in a system with zero momentum, where it can be weighed. It is also equivalent to mass, and this mass is always associated with it. Mass is also equivalent to a certain amount of energy, and likewise always appears associated with it, as described in mass, energy equivalence. Part of the rest energy, equivalent to rest mass, of matter may be converted to other forms of energy, still exhibiting mass, but neither energy nor mass can be destroyed, rather, both remain constant during any process. However, since C2 is extremely large relative to ordinary human scales, the conversion of an everyday amount of rest mass, for example, 1 kilogram, from rest energy to other forms of energy, such as kinetic energy, thermal energy, or the radiant energy carried by light and other radiation, can liberate tremendous amounts of energy, 9 times 10^16 joules, equivalent to 21 megatons of TNT, as can be seen in nuclear reactors and nuclear weapons. Conversely, the mass equivalent of an everyday amount energy is minuscule, which is why a loss of energy, loss of mass, from most systems is difficult to measure on a weighing scale, unless the energy loss is very large. Examples of large transformations between rest energy, of matter, and other forms of energy, example kinetic energy into particles with rest mass, are found in nuclear physics and particle physics. Often, however, the complete conversion of matter, such as atoms, to non-matter, such as photons, is forbidden by conservation laws. Thermodynamics divides energy transformation into two kinds, reversible processes and irreversible processes. An irreversible process is one in which energy is dissipated, spread, into empty energy states available in a volume, from which it cannot be recovered into more concentrated forms, fewer quantum states, without degradation of even more energy. A reversible process is one in which this sort of dissipation does not happen. For example, conversion of energy from one type of potential field to another is reversible, as in the pendulum system described above. In processes where heat is generated, quantum states of lower energy, present as possible excitations in fields between atoms, act as a reservoir for part of the energy, from which it cannot be recovered, in order to be converted with 100% efficiency into other forms of energy. In this case, the energy must partly stay as thermal energy and cannot be completely recovered as usable energy, except at the price of an increase in some other kind of heat, like increase in disorder in quantum states, in the universe, such as an expansion of matter, or a randomization in a crystal. As the universe evolves with time, more and more of its energy becomes trapped in irreversible states, i.e., as heat, or as other kinds of increases in disorder. This has led to the hypothesis of the inevitable thermodynamic heat death of the universe. In this heat death, the energy of the universe does not change, but the fraction of energy which is available to do work through a heat engine, or be transformed to other usable forms of energy, through the use of generators attached to heat engines, continues to decrease. The fact that energy can be neither created nor destroyed is called the law of conservation of energy. In the form of the first law of thermodynamics, this states that a closed system's energy is constant unless energy is transferred in or out as work or heat, and that no energy is lost in transfer. The total inflow of energy into a system must equal the total outflow of energy from the system, plus the change in the energy contained within the system. Whenever one measures, or calculates, the total energy of a system of particles whose interactions do not depend explicitly on time, it is found that the total energy of the system always remains constant. While heat can always be fully converted into work in a reversible isothermal expansion of an ideal gas, for cyclic processes of practical interest in heat engines, the second law of thermodynamics states that the system doing work always loses some energy as waste heat. This creates a limit to the amount of heat energy that can do work in a cyclic process, a limit called the available energy. Mechanical and other forms of energy can be transformed in the other direction into thermal energy without such limitations. The total energy of a system can be calculated by adding up all forms of energy in the system. Thank you for watching this video.